Far beyond the familiar glow of our closest planets, in regions of space so distant that sunlight barely whispers across their frozen surfaces, ancient travelers drift in patient orbits that have continued for billions of years. These are comets, and they move through darkness with a quietness that defies imagination. Each one carries within its icy heart a record of our solar system's earliest moments, preserved in frozen gases and dust that have remained largely unchanged since the time when planets were still forming from clouds of cosmic debris. A comet in deep space is nothing like the dramatic apparitions we sometimes observe from Earth. Out there, in the cold reaches beyond Neptune, a comet is simply a dark body of ice and rock, tumbling slowly through the void without fanfare or spectacle. It reflects almost no light. Its surface, darker than coal with an albedo of just 0.04, absorbs rather than reflects the faint radiation that reaches it. If you could, somehow, stand on one of these distant shores, the sun would appear as merely the brightest star in a sky full of stars, offering no warmth, creating no shadows, demanding nothing of the silent ice beneath your feet. The nucleus of a typical comet measures somewhere between a few kilometers and perhaps 20 or 30 kilometers across. To put this in perspective, if you were to walk around the equator of a 10-kilometer wide comet at a comfortable pace, your journey would take you only a few hours to complete. These are not massive worlds. They are more like mountains or small hills, adrift in an ocean of empty space. Yet within these modest dimensions lies material that predates the Earth itself, substance that condensed from the solar nebula 4.6 billion years ago, when our star was newly born and the region we now call the solar system was still a disk of gas and dust swirling in the darkness. Tonight, as you settle into rest, we will explore these wanderers together. We will move slowly through facts and figures that speak to the gentle nature of comets, their patient orbits, their quiet transformations. There will be no urgency here, no dramatic revelations demanding your attention. Instead, think of this as a slow journey through deep space, where time moves differently, where changes unfold across millennia rather than moments, where the simple fact of existence is enough. You might find yourself drifting as we talk about these frozen bodies. That is perfectly acceptable. In fact, it is encouraged. The information will continue to flow whether you are listening actively or allowing the words to simply wash over you like a gentle tide. There is no test at the end, no requirement that you remember specific numbers or names. This is simply an exploration, conducted at the pace of deep space itself, where nothing rushes and everything endures. Comets have been observed by human beings for thousands of years. Ancient astronomers tracked their appearances with a mixture of wonder and trepidation, not understanding what these visitors were or where they came from. In many cultures, comets were seen as omens, harbingers of significant events. But we now know they are not omens at all. They are simply travelers, following the physics of gravity and motion, responding to forces that act upon them, just as those same forces act upon planets, moons, and every other body in our solar system. The word comet comes from the Greek comets, meaning long-haired. This ancient description captures something essential about how comets appear when they venture close to the sun and develop their characteristic tails. But that flowing hair is a temporary condition, a brief transformation that occurs only when a comet's elliptical orbit carries it into the inner solar system. For most of a comet's existence, there is no hair, no tail, no glowing coma. There is only the nucleus, that small, dark, frozen body tumbling through space in patient solitude. When we look at a bright comet in Earth's sky, what we are actually seeing is the result of ice turning directly from solid to gas, a process called sublimation. This happens when solar radiation warms the comet's surface enough to release frozen volatiles. But this is getting ahead of ourselves. For now, simply know that comets spend most of their time in a state of frozen quietude, far from the sun, unchanged and unchanging, drifting through orbits that may take them hundreds or even thousands of years to complete. The solar system is vastly larger than most people realize. We tend to think of it as extending perhaps to Neptune or maybe to Pluto, the former planet that orbits at about 30 to 50 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, roughly 93 million miles or 150 million kilometers. But the solar system does not end at Pluto. It extends much, much farther. Out beyond the Kuiper Belt, beyond the scattered disk, there lies a region called the Oort cloud, a theoretical sphere of icy bodies that surrounds our entire solar system. This cloud begins at perhaps 2,000 astronomical units from the Sun and extends outward to perhaps 100,000 astronomical units. To give you a sense of scale, if you could travel at the speed of light, it would take you 8 minutes to reach the Sun from Earth, but it would take you nearly a year and a half to reach the outer edge of the Oort cloud. This is where many comets spend the vast majority of their existence, in a frozen realm so distant that the Sun is barely distinguishable from other stars. In this outer darkness, temperatures hover only a few degrees above absolute zero. There is no wind, of course. There is no weather. There is only the endless radiation of heat into the void, the gentle tug of gravity, and the slow, patient movement of bodies in their ancient orbits. A comet in the Oort cloud might take millions of years to complete a single orbit around the Sun. During all that time, nothing about it changes. The ice remains ice. The dust remains dust. The nucleus tumbles slowly, absorbing negligible warmth from distant starlight, radiating that same negligible warmth back into space. And yet, occasionally, something shifts. Perhaps a passing star exerts a gravitational influence. Perhaps 2 comets pass near enough to each other that their mutual gravity alters their paths. Perhaps the combined pull of the galaxy itself nudges a comet's orbit inward. Whatever the cause, sometimes a comet that has been quietly orbiting in the outer reaches begins a long, slow fall toward the inner solar system. This journey might take thousands of years. The comet does not speed up suddenly. It accelerates gradually, imperceptibly, following the mathematics of orbital mechanics, responding to the Sun's gravity pulling it forward and inward. As it falls, the comet remains frozen. Even at distances of 50 or 100 astronomical units, the Sun's warmth is far too weak to affect the surface ice. The comet continues its patient tumble, reflecting almost no light, visible to no one, a dark speck against the darkness of space. And so it continues, kilometer after kilometer, year after year, century after century, falling in silence toward the star at the center of everything. There is something deeply peaceful about this image. A mountain of ice and rock tumbling through the dark, changing nothing, demanding nothing, simply following the path that physics has laid out for it. No consciousness guides it. No will propels it forward. It moves because it must move, held in the gentle but inexorable grasp of gravity, making its long journey from outer darkness toward eventual light. At the heart of every comet lies the nucleus, the solid body that defines what the comet is. When a comet is far from the Sun, the nucleus is essentially the entire comet. There is no coma, no tail, no glowing atmosphere. There is only this dark, frozen body, composed of materials that have remained largely unchanged since the solar system's formation. The composition of a cometary nucleus is predominantly water ice. Studies of several comets suggest that approximately 75 to 80% of the nucleus consists of frozen water. This is water ice in its most fundamental form, H2O molecules locked into crystalline structures by the extreme cold of deep space. But water ice is not the only component. Mixed throughout the nucleus are other frozen volatiles, compounds that remain solid at the temperatures found in the outer solar system, but which will sublimate into gas if sufficiently warmed. Carbon monoxide ice comprises perhaps 10 to 15% of a typical nucleus. This compound, consisting of one carbon atom bonded to one oxygen atom, freezes at temperatures below -191 degrees Celsius. In the depths of the Oort cloud, or the Kuiper belt, carbon monoxide remains solidly frozen, mixed intimately with water ice and other materials. Carbon dioxide, the familiar greenhouse gas that exists in Earth's atmosphere, is also present, though in smaller quantities. Frozen methane, ammonia, and other organic compounds round out the volatile components of the nucleus. Embedded within and mixed throughout these ices are dust and rock. These refractory materials make up perhaps 20 to 25% of the nucleus. The dust particles range in size from microscopic grains only a few micrometers across to larger chunks, perhaps a few millimeters in diameter. Some of this dust consists of silicate minerals, compounds of silicon and oxygen that are common throughout the solar system. Other dust particles contain organic compounds, complex molecules built from carbon, hydrogen, oxygen, nitrogen, and other elements. The nucleus is not a solid, monolithic block of ice. Rather, it has a porous structure, somewhat like a sponge, or a pile of loosely compacted snow. The bulk density of a cometary nucleus is typically around 600 kilograms per cubic meter. To put this in perspective, solid water ice has a density of about 900 kilograms per cubic meter, while solid rock has densities ranging from 2,000 to 3,000 kilograms per cubic meter. The relatively low density of cometary nuclei indicates that they contain significant amounts of empty space, voids, and gaps within the structure where there is literally nothing at all. This porous nature has important implications. It means that a comet's nucleus is quite fragile. It is not a solid boulder of ice that could withstand significant impacts or stresses. Rather, it is more like a loosely bound collection of icy chunks held together primarily by their own weak gravity and by the frozen ices that fill the spaces between them. If you could somehow squeeze a cometary nucleus in your hand, it might crumble like a snowball rather than resist like a rock. The surface of a cometary nucleus is covered with a layer of dark material. This crust consists primarily of dust and organic compounds that have been left behind as ice near the surface has sublimated away over multiple passages through the inner solar system. The ices sublimate, turning directly from solid to gas and escaping into space, but the dust and larger particles are too heavy to be lifted away by the escaping gas. They accumulate on the surface, forming a layer that can be 20 centimeters thick or more. This dark crust is remarkably non-reflective. The albedo of a typical cometary nucleus is around 0.03 to 0.04. This means that only 3 to 4% of the light that falls on the surface is reflected back into space. The rest is absorbed. For comparison, fresh snow has an albedo of about 0.8 to 0.9, reflecting 80 to 90% of incoming light. Coal has an albedo of about 0.07. Cometary nuclei are darker than coal. They are among the darkest objects in the entire solar system. Why is this surface so dark? The answer lies in the nature of the organic compounds that accumulate there. As ices sublimate, they carry away lighter molecules, leaving behind heavier, more complex organic compounds. These compounds, which may include long-chain hydrocarbons and other carbon-rich molecules, tend to be very dark in color. Over time, as sublimation continues, these materials concentrate on the surface, creating a dark lag deposit that covers the underlying ice. The shape of a cometary nucleus is typically irregular. Unlike planets, which are large enough for their own gravity to pull them into spherical shapes, comets are too small for this process to occur. Instead, cometary nuclei often resemble potatoes or peanuts, with elongated forms and uneven surfaces. The nucleus of Halley's Comet, for example, measures approximately 15 kilometers by 8 kilometers by 8 kilometers, giving it a distinctly elongated appearance. Some cometary nuclei are even more irregular. The nucleus of Comet 67P/Churyumov-Gerasimenko, which was extensively studied by the European Space Agency's Rosetta mission, has a remarkable shape that has been described as resembling a rubber duck. It consists of two distinct lobes connected by a narrow neck region. This peculiar shape may have resulted from a gentle collision between two separate cometary bodies in the distant past, a collision so slow and gentle that instead of shattering both bodies, it simply caused them to stick together. The rotation of a cometary nucleus is another aspect of its character. Like all bodies in space, cometary nuclei rotate around their axes. The rotation period varies from comet to comet. Some nuclei rotate quite rapidly, completing a full rotation in just a few hours. Others rotate more slowly, taking a day or more to complete one turn. This rotation is not usually smooth and steady like the rotation of a planet. Instead, because of the irregular shape and uneven mass distribution of the nucleus, the rotation can be complex, with the body tumbling in ways that make it difficult to define simple poles of rotation. As a nucleus rotates, different parts of its surface are exposed to sunlight when the comet is in the inner solar system. This creates patterns of heating and cooling that drive sublimation in complex ways. Areas that face the sun warm up and begin to release gas and dust. Areas in shadow cool down and sublimation ceases. This creates jets and outbursts that are not uniformly distributed around the nucleus, but instead emerge from specific active regions where ice is exposed or where the overlying dust layer is thin enough to allow sublimation to occur. Temperature is another key characteristic of the nucleus. When a comet is in the distant reaches of the solar system, far from the sun, the surface temperature of the nucleus is extremely cold, perhaps only 30 or 40 Kelvin. This is 40 degrees above absolute zero, or roughly minus 230 degrees Celsius. At these temperatures, all volatiles remain solidly frozen. Nothing sublimates, nothing changes. The nucleus simply exists in a state of frozen equilibrium with its environment. As a comet falls inward toward the sun, its surface temperature gradually increases. By the time the comet reaches the distance of Jupiter's orbit, about 5 astronomical units from the sun, the surface temperature has risen to perhaps 150 to 170 Kelvin. This is still far below the freezing point of water by terrestrial standards, but it is warm enough for some of the more volatile ices, such as carbon monoxide, to begin sublimating. The nucleus of a comet can survive many passages through the inner solar system. Each time it approaches the Sun, it loses some of its mass to sublimation. The outer layers of ice vaporize and escape, carrying dust with them, slowly eroding the nucleus over time. For a typical comet, the mass loss rate during perihelion passage, when it is closest to the Sun, might be on the order of 10,000 kilograms per second. This sounds like a lot, but consider that a nucleus with a radius of 5 kilometers and an average density of 600 kilograms per cubic meter has a total mass of about 300 billion kilograms. At a loss rate of 10,000 kilograms per second, the comet could sustain active sublimation for about 1 million seconds, or roughly 12 days, before losing even 1% of its mass. Of course, comets do not sublimate continuously. They sublimate only when they are close enough to the Sun for temperatures to rise sufficiently. For a comet with a short period orbit, such as a Jupiter family comet that orbits the Sun every few years, this might mean a few weeks of significant activity with each orbit. For a long-period comet that takes thousands of years to orbit the Sun, active sublimation might occur only for a year or two out of that entire orbital period. The rest of the time, the nucleus remains frozen and inert. Eventually, after many orbits, a comet will exhaust its volatile ices. The outer layers will have been stripped away, leaving behind only the refractory dust and rock that were mixed with the ice. At this point, the object is no longer capable of developing a coma or tails. It has become, effectively, an asteroid. This process is thought to be the fate of many comets, gradually transitioning from active comets to dormant or extinct comets that no longer exhibit any cometary activity. But for most comets, this endpoint lies far in the future. The typical comet we observe today has enough volatile material to continue its cycle of activity for hundreds or thousands of orbits. And so the nucleus continues its journey, sometimes active and glowing with sublimating gases, sometimes dormant and dark, but always patient, always following the orbital path that physics dictates, always carrying within itself that ancient record of our solar system's formation, preserved in ice and dust. There comes a point in a comet's inward journey when transformation begins. This does not happen suddenly. There is no single moment when a comet changes from one state to another. Instead, the transformation is gradual, almost imperceptibly slow at first, building over time as the comet continues to fall toward the Sun and temperatures at its surface continue to rise. Sublimation is the key process that drives this transformation. Sublimation is the transition of a substance directly from solid to gas, bypassing the liquid phase entirely. We are familiar with this process on Earth, where dry ice, frozen carbon dioxide, sublimates at normal atmospheric pressure, turning directly from solid to gas without ever becoming liquid. In the vacuum of space, all ices behave this way. When they are warmed sufficiently, they sublimate, their molecules breaking free from the solid structure and escaping into space as gas. For a comet, sublimation typically begins when it reaches a distance of about 5 astronomical units from the Sun, roughly the distance of Jupiter's orbit. At this distance, solar radiation has warmed the surface to temperatures where the most volatile compounds, such as carbon monoxide and carbon dioxide, can begin to sublimate. Water ice, which is less volatile, does not begin significant sublimation until the comet reaches a distance of about 3 astronomical units inside the orbit of Mars. When sublimation begins, molecules of gas escape from the surface of the nucleus. Because the comet's gravity is so weak, These molecules do not fall back to the surface as they would on a larger body like Earth. Instead, they continue moving outward, away from the nucleus, at speeds of several hundred meters per second. As more and more molecules escape, they create a cloud of gas around the nucleus. This cloud is called the coma. The coma grows as sublimation continues. Gas molecules escaping from the nucleus push outward in all directions, expanding into the vacuum of space. The coma has no distinct boundary. It simply becomes less and less dense as you move farther from the nucleus, gradually fading into the background of interplanetary space. But near the nucleus, the density of gas can be significant, creating a temporary atmosphere around the comet. The size of the coma depends on how much gas is being released and on how far the comet is from the Sun. A comet at a distance of 2 astronomical units from the Sun might develop a coma 100,000 kilometers in diameter. As the comet continues inward, approaching a distance of 1 astronomical unit, the perihelion distance of many comets, the coma can grow to several 100,000 kilometers across. Some particularly active comets develop comas that exceed 1 million kilometers in diameter, larger than the Sun itself. To give you a sense of scale, Earth's diameter is about 12,700 kilometers. A coma 100,000 kilometers across is nearly 8 times the diameter of Earth. A coma 1 million kilometers across is nearly 3 times the diameter of the Sun. And yet, despite these enormous dimensions, the coma is extraordinarily tenuous. The density of gas in the coma is far lower than the best vacuum we can create in laboratories on Earth. If you could somehow stand within the coma, you would perceive yourself to be in empty space. You would see nothing, feel nothing. Only sensitive instruments could detect the presence of gas molecules. The composition of the coma reflects the composition of the nucleus. Water vapor is the dominant component in most comets, accounting for perhaps 80 to 90% of the gas in the coma. Carbon monoxide and carbon dioxide are the next most abundant species, followed by smaller amounts of methane, ammonia, and various organic molecules. As this gas expands away from the nucleus, it is exposed to solar radiation. Ultraviolet light from the Sun contains enough energy to break apart molecules and to knock electrons free from atoms, a process called photoionization. When a water molecule absorbs a high-energy ultraviolet photon, the molecule can break apart into hydrogen and hydroxyl radicals. The hydrogen atoms, being extremely light, quickly escape the coma entirely, expanding outward to form a vast hydrogen envelope that can extend for millions of kilometers beyond the visible coma. This hydrogen envelope is not visible to the naked eye, but it can be detected using instruments sensitive to ultraviolet light. Meanwhile, the heavier molecules and molecular fragments remain in the inner coma. Some of these molecules fluoresce when they absorb solar radiation, emitting visible light at specific wavelengths. This fluorescence is what makes the coma visible from Earth. Different molecules emit light at different colors. Diatomic carbon, for example, emits green light. Cyanogen emits blue light. The combination of emissions from various molecules gives the coma its characteristic color, often a greenish or bluish tinge. The coma is not perfectly symmetrical. Sublimation does not occur uniformly across the entire surface of the nucleus. Instead, it is concentrated in active regions where ice is exposed or where the overlying dust layer is thin. As the nucleus rotates, these active regions rotate with it, creating spirals and jets in the coma as gas is released in specific directions. From Earth, when we observe a comet through a telescope, we can sometimes see these spiral structures in the inner coma, evidence of the nucleus rotating beneath its temporary atmosphere. The process of sublimation also releases dust. The dust particles, which were embedded in the ice of the nucleus, are carried along by the expanding gas. However, dust particles are much heavier than gas molecules and they do not move as quickly. While gas molecules might leave the nucleus at speeds of several hundred meters per second, dust particles typically move at speeds of only a few meters per second to a few tens of meters per second, depending on their size. Smaller dust particles, those with diameters less than a micrometer, are more easily accelerated by the gas flow and can reach higher speeds. Larger particles, those with diameters of a millimeter or more, are barely lifted off the surface at all. They may hop across the surface or be carried along for a short distance before falling back to the nucleus. The intermediate-sized particles, those with diameters in the range of micrometers to hundreds of micrometers, are the ones that contribute most to the visible dust component of the coma and eventually to the dust tail. As dust particles move away from the nucleus, they are affected by sunlight in a different way than gas molecules. While gas molecules are primarily ionized by ultraviolet radiation, dust particles are affected by the pressure of sunlight itself, a phenomenon called radiation pressure. When a photon of light strikes a dust particle, it transfers a tiny amount of momentum to the particle, pushing it in the direction the light was traveling. For small particles, this radiation pressure can be significant, eventually overwhelming the weak gravity of the nucleus and pushing the dust particles away from the sun. The coma, then, is a complex and dynamic environment. It consists of gas molecules moving rapidly outward, dust particles moving more slowly, all of this expanding into space while being continually replenished by sublimation from the nucleus below. The coma is constantly changing as the nucleus rotates, as the comet moves along its orbit, and the intensity of solar radiation changes, and as different volatiles begin or cease sublimating depending on the temperature. And yet, for all its complexity, the coma has a certain tranquility to it. The gas molecules do not collide with each other very often because the density is so low. They simply drift outward, expanding into the vacuum, moving in gentle curves influenced by the pressure of sunlight and the solar wind. The dust particles follow similar gentle paths, slowly accelerating away from the nucleus, gradually spreading out to form a cloud that catches and reflects sunlight, making the coma visible from vast distances. For someone observing a comet from Earth, the coma appears as a fuzzy ball of light surrounding a brighter central region where the nucleus is located. The coma does not have sharp edges. It fades gradually into the darkness of space. Its appearance is peaceful, soft, a gentle glow in the night sky. There is none of the harshness of a star's point of light, none of the solidity of a planet's disk. The coma is more like a cloud, ethereal and impermanent, existing only because sublimation continues to feed it with gas and dust from the nucleus below. As the comet continues its journey around the sun and eventually begins moving outward again, the rate of sublimation decreases. The surface temperature drops. Volatiles that were sublimating cease to do so. The coma begins to shrink, becoming smaller and less dense as the supply of new gas dwindles. Eventually, when the comet has moved far enough from the sun, sublimation stops entirely. The coma dissipates, its molecules and dust particles spreading out into interplanetary space. The nucleus returns to its frozen state, dark and inactive, tumbling silently through space until its next passage through the inner solar system, perhaps decades or centuries in the future. As sublimation continues and the coma grows, a comet begins to develop another characteristic feature: its tail. Or more precisely, its tails. For most comets that develop tails actually develop two distinct tails, each formed by different processes and each with its own character and appearance. The first tail to consider is the dust tail. As we discussed, dust particles are carried away from the nucleus by the expanding gas of the coma. These particles, ranging in size from micrometers to millimeters, move outward into space, but they do not move in straight lines directly away from the nucleus. Instead, their paths are curved, bent by the pressure of sunlight pushing them away from the sun. Radiation pressure acts on dust particles because light, though it has no mass, carries momentum. When a photon of light strikes a dust particle, it transfers a tiny amount of momentum to that particle. For small particles, this radiation pressure is surprisingly strong, strong enough to overcome the weak gravitational pull of the sun and push the particles into paths that curve away from the sun's direction. The effect of radiation pressure depends on the size of the dust particles. Smaller particles, those with diameters around 1 micrometer, are most strongly affected. They experience a higher ratio of radiation pressure force to gravitational force and are pushed more strongly away from the sun. Larger particles, those with diameters of a millimeter or more, are less affected by radiation pressure relative to their mass, and their paths are less strongly curved. The result of this size-dependent acceleration is that the dust tail develops a characteristic curved shape. The dust particles that were released from the nucleus when the comet was farther from the sun have traveled farther and have had more time to be affected by radiation pressure. They form the outer, more widely spread portions of the tail. The dust particles released more recently are still closer to the head of the comet, forming the inner, brighter portions of the tail. The overall effect is a broad, curved tail that sweeps back from the comet's head, curving away from the direction of the sun, but also curving back slightly in the direction the comet came from. The dust tail can be extraordinarily long. In some bright comets, the dust tail can extend for tens of millions of kilometers, sometimes even more than 100 million kilometers. To put this in perspective, the distance from Earth to the Sun is about 150 million kilometers. A dust tail 100 million kilometers long would stretch nearly 2/3 of the way from Earth to the Sun. Seen from Earth, such a tail can stretch across significant portions of the sky, sometimes spanning 30 or 40 degrees from one end to the other. The dust tail reflects sunlight, which is how we see it. The dust particles scatter sunlight in all directions, and some of that scattered light reaches Earth, making the tail visible. The color of the dust tail is typically white or yellowish, reflecting the color of the sun's light. The brightness of the dust tail depends on how much dust is being produced by the comet and on the size distribution of the dust particles. Comets that produce large amounts of small dust particles tend to have brighter, more prominent dust tails. The second tail is the ion tail, also called the gas tail or plasma tail. This tail is formed not from dust, but from gas molecules that have been ionized by solar radiation. When ultraviolet light from the sun strikes a molecule in the coma, it can knock an electron free from that molecule, leaving behind a positively charged ion. These ions are affected by the solar wind. The solar wind is a stream of charged particles, primarily protons and electrons, flowing outward from the sun at speeds of several hundred kilometers per second. The solar wind carries with it the sun's magnetic field, which is embedded in the plasma of charged particles. This magnetic field interacts with the ions in the comet's coma, sweeping them directly away from the sun in the direction of the solar wind flow. Because the solar wind is moving much faster than the comet, the ion tail is pushed straight back from the head of the comet, pointing almost exactly away from the sun. Unlike the curved dust tail, the ion tail is straight or nearly straight, a narrow stream of ionized gas extending outward from the coma. The length of the ion tail can be enormous. Some comets develop ion tails that stretch for hundreds of millions of kilometers, even exceeding 1 astronomical unit in length. The ion tail is visible not because it reflects sunlight, but because the ions themselves emit light through a process called fluorescence. When ions absorb energy from solar radiation or from collisions with other particles in the solar wind, they can be excited to higher energy states. When they return to lower energy states, they emit photons at specific wavelengths. The most prominent emission in many comet ion tails comes from ionized carbon monoxide, which emits blue light. As a result, ion tails often appear blue or bluish-white in color photographs. The ion tail is more dynamic than the dust tail. Because it is directly influenced by the solar wind, which can vary in intensity and direction, the ion tail can change rapidly. Sometimes, the solar wind carries a region of oppositely directed magnetic field, creating conditions where the magnetic field lines in the ion tail reconnect in a process called magnetic reconnection. When this happens, a section of the ion tail can actually disconnect from the comet, drifting away into space while a new ion tail begins to form from the coma. These disconnection events have been observed in several comets and provide dramatic evidence of the interaction between comets and the solar wind. Not all comets develop both tails. Whether a comet develops prominent tails depends on how much gas and dust it produces, which in turn depends on how active it is and how close it approaches the Sun. A small, weakly active comet might develop only a modest coma with no visible tail at all. A large, highly active comet approaching close to the Sun can develop spectacular tails that dominate the sky. The orientation of the tails is always related to the Sun's direction. Both tails point generally away from the Sun, though the dust tail curves and the ion tail points more directly away. This means that when a comet is approaching the Sun in its orbit, the tails trail behind the comet's nucleus. But when the comet has passed perihelion and is moving outward, away from the Sun, the tails actually precede the nucleus, pointing outward along the direction the comet is moving. This seems counterintuitive at first, but it is simply a consequence of the fact that the tails point away from the Sun, not away from the direction of motion. There is also a phenomenon called an anti-tail or sunward tail, which can occasionally be observed. This is not actually a tail pointing toward the Sun, but rather an optical illusion created when Earth's viewing angle allows us to see particles in the comet's orbital plane that lie on the sunward side of the nucleus. These particles were ejected from the comet earlier in its orbit and have spread along the comet's path. When we view them edge-on from Earth, they appear as a spike pointing toward the Sun. This effect is usually visible for only a short time as Earth passes through the plane of the comet's orbit. The tails of a comet are ephemeral structures. They exist only as long as the comet continues to produce gas and dust, and only as long as the Sun's radiation and solar wind continue to act upon those materials. The particles that make up the tails are constantly being replenished from the nucleus and constantly drifting away into interplanetary space. Once a particle leaves the coma and enters a tail, it is essentially on its own, following a trajectory determined by radiation pressure and solar wind, no longer influenced by the nucleus from which it came. Over time, these particles spread throughout the inner solar system. Dust particles from comets contribute to the zodiacal light, a faint glow visible in the night sky along the plane of the ecliptic. Ion molecules eventually merge with the general background of the interplanetary medium. In this way, comets gradually distribute their material throughout the solar system, losing mass with each passage through the inner regions, slowly being eroded away by the very processes that make them visible and beautiful. But this erosion is slow, measured in thousands or millions of years for most comets. In the span of a single human lifetime, a comet returns and returns again, developing its tails with each close approach to the Sun, then retreating into the cold darkness where the tails dissipate and the nucleus returns to its frozen state. The cycle continues, patient and predictable, governed by the mathematics of orbital mechanics and the physics of sublimation and ionization. When we observe a comet with its tails streaming away from the Sun, we are witnessing a transformation that has occurred countless times throughout the history of our solar system. These same processes shaped the ancient comets that fell toward the Sun 4 billion years ago, when Earth was young and life had not yet emerged. The physics has not changed. The beauty has not diminished. The tails still stream away from the Sun, still catch the light, still mark the presence of these ancient wanderers as they make their patient way through the darkness of space. To understand where comets come from, we must travel in our minds to the edges of the solar system and beyond, to regions so distant that they test the limits of imagination. These are the reservoirs where comets reside when they are not visiting the inner solar system, cold storage regions where icy bodies have orbited for billions of years, largely unchanged since the era of planetary formation. The first of these reservoirs is the Kuiper Belt, a region that begins just beyond the orbit of Neptune, at about 30 astronomical units from the Sun and extends outward to perhaps 50 astronomical units. This is a flattened disk of icy bodies orbiting the Sun in roughly the same plane as the planets. The existence of the Kuiper Belt was proposed in 1951 by Gerard Kuiper, who suggested that a belt of cometary material must exist beyond Neptune to explain the population of short-period comets. The Kuiper Belt was not directly observed until 1992, when astronomers David Jewett and Jane Liu discovered the first Kuiper Belt object beyond Pluto. Since then, thousands of Kuiper Belt objects have been catalogued, ranging in size from small cometary nuclei just a few kilometers across to dwarf planets like Pluto itself, which has a diameter of about 2,340 kilometers. Objects in the Kuiper Belt orbit the Sun on relatively circular paths with orbital periods of a few hundred years. They remain in the cold outer regions of the solar system, where temperatures are so low that even highly volatile ices remain frozen. These objects are thought to be remnants from the era of planetary formation, planetesimals that never accreted into a planet because the density of material in this region was too low, and Neptune's gravity prevented them from coalescing into a larger body. Short-period comets, those with orbital periods less than 200 years, are thought to originate primarily from the Kuiper Belt or from a related region called the scattered disk. The scattered disk consists of objects whose orbits were significantly altered by gravitational interactions with Neptune, giving them more elongated and inclined orbits that carry them far beyond the main Kuiper Belt. These scattered disk objects occasionally have their orbits perturbed further, sending them into the inner solar system where they become observable as comets. The process by which a Kuiper Belt object becomes a comet involves a gradual change in its orbit. Perhaps a close approach to Neptune alters the orbit slightly, making it more elongated. Perhaps gravitational interactions with other Kuiper Belt objects over millions of years gradually shift the orbit inward. Whatever the mechanism, eventually the object's orbit takes it close enough to the Sun that sublimation begins. At that point, it is no longer simply a Kuiper Belt object. It has become a comet. Jupiter family comets, a subset of short-period comets with orbital periods less than about 20 years, are thought to come specifically from the scattered disk. These comets have orbits that are closely aligned with the plane of the ecliptic, reflecting their origin in the flat disk of the Kuiper belt. Examples include Comet 67P/Churyumov-Gerasimenko, which was visited by the Rosetta spacecraft, and Comet 9P/Tempel 1, which was the target of NASA's Deep Impact mission. Beyond the Kuiper belt, far beyond, lies the Oort cloud. This is a theoretical sphere of cometary bodies surrounding the entire solar system at distances ranging from perhaps 2,000 astronomical units to perhaps 100,000 astronomical units. To give some sense of this scale, the Kuiper belt lies at 30 to 50 astronomical units from the Sun. The Oort cloud begins at 2,000 astronomical units, more than 40 times farther away, and extends outward to 100,000 astronomical units, more than 2,000 times farther than Neptune. At these distances, the Sun appears as merely the brightest star in the sky. Its gravitational influence is weak, but it is still sufficient to bind these distant objects in orbit. The orbital periods of Oort cloud comets can exceed millions of years. During a single orbit, human civilizations rise and fall, species evolve and go extinct, continents drift, and mountains erode. The comet simply continues its patient orbit, so far from the Sun that nothing about it changes from one millennium to the next. The Oort cloud was proposed in 1950 by Dutch astronomer Jan Oort, who noticed that long-period comets, those with orbital periods greater than 200 years, seem to come from all directions in space rather than being confined to the plane of the ecliptic. This suggested that they originated from a spherical distribution of objects surrounding the Sun rather than from a flattened disk like the Kuiper belt. The Oort cloud is divided into two regions. The inner Oort cloud, also called the Hills cloud, after Jack Hills, who studied it, is thought to be a thick disk extending from perhaps 2,000 to 20,000 astronomical units from the Sun. The outer Oort cloud is a spherical shell extending from 20,000 to 100,000 astronomical units. The total number of comets in the Oort cloud is thought to be in the trillions, with a combined mass perhaps equivalent to a few Earth masses. How did the Oort cloud form? Current theories suggest that the objects now in the Oort cloud did not form where they currently reside. Instead, they formed much closer to the Sun, in the region where the giant planets now orbit. During the early history of the solar system, when the planets were still migrating and settling into their current orbits, gravitational interactions with Jupiter and Saturn flung many icy planetesimals outward with tremendous force. Some of these objects were ejected from the solar system entirely, sent into interstellar space on hyperbolic orbits. Others were flung into very distant orbits but remained gravitationally bound to the Sun. Over time, as the solar system passed through the galactic disk and as nearby stars occasionally passed within a few light years of the Sun, the orbits of these distant objects were perturbed and randomized, creating the spherical distribution we call the Oort cloud. Long-period comets originate from the Oort cloud. These comets typically have highly elongated orbits with very large semi-major axes. When their orbits are perturbed by passing stars or by the galactic tide, the tide of gravitational force exerted by the disk of the Milky Way galaxy itself, some of these comets have their perihelia lowered, bringing them into the inner solar system for the first time in billions of years. These first-time visitors from the Oort cloud are sometimes called dynamically new comets. They are interesting because they are visiting the inner solar system for the first time and have not been significantly altered by previous passages near the Sun. Their surfaces have not been covered with the dark lag deposit that forms on comets that have made multiple passages. Their volatile content is pristine, unaltered since the era of solar system formation. Many famous comets are long-period comets from the Oort cloud. Comet Hale-Bopp, which was spectacularly visible in 1997, has an orbital period of about 2,530 years and originates from the Oort cloud. Comet Hyakutake, which passed close to Earth in 1996, has an orbital period exceeding 10,000 years. These comets make single visits to the inner solar system, their appearances rare and unpredictable from the human perspective. The journey of a long-period comet from the Oort cloud to the inner solar system is a journey of thousands or millions of years. The comet begins its fall slowly, imperceptibly, its orbit gradually shifting inward over eons. As it falls, it accelerates, gaining speed as the Sun's gravitational pull grows stronger. By the time it reaches the inner solar system, it may be moving at speeds of tens of kilometers per second, falling toward the Sun like a stone dropped from an immense height. But even at these speeds, the inward journey takes time. A comet beginning its journey from 50,000 astronomical units would take millions of years to reach perihelion. During all this time, it remains frozen, dark, unobservable. Only when it reaches distances of a few astronomical units from the Sun does sublimation begin and the comet develop a coma that makes it visible. After its brief period of visibility, lasting perhaps a few months to a year, as it passes through the inner solar system, the long-period comet swings around the Sun and begins its long journey back out into the darkness. Its orbit carries it outward at speeds that gradually decrease as the Sun's gravity slows it, pulling it back. Over thousands or millions of years, the comet climbs back up the gravitational well, moving farther and farther from the Sun until eventually it reaches aphelion, the farthest point of its orbit in the cold darkness of the Oort cloud. And there it remains, frozen and unchanging, for another orbital period that may last longer than human civilization has existed. The cycle continues, slow and patient, governed by the same gravitational forces that have shaped the solar system for 4.6 billion years. The Oort cloud and Kuiper belt are reservoirs of ancient material, storehouses of icy bodies that have remained largely unchanged since the solar system's youth, waiting in cold darkness for their rare opportunities to venture inward and briefly grace the skies of Earth with their presence. The discovery and study of Kuiper belt objects has provided direct evidence for the existence of this reservoir. Before 1992, the Kuiper belt was purely theoretical, inferred from the existence and properties of short-period comets. But the discovery of the first Kuiper belt object, now designated as 15,760 Albion, confirmed that this region of space does indeed contain a significant population of icy bodies. Since then, the catalogue of known Kuiper belt objects has grown to include thousands of confirmed discoveries, and likely hundreds of thousands of objects awaiting detection. The largest known Kuiper belt objects are actually classified as dwarf planets. Pluto, once considered the 9th planet, is now understood to be the largest known member of the Kuiper belt, with a diameter of about 2,340 kilometers. Eris, discovered in 2005, is slightly smaller in diameter but more massive than Pluto. Makemake, Haumea, and other large Kuiper belt objects continue to be discovered and studied, revealing a population of worlds that straddles the boundary between comets and planets. These large Kuiper belt objects show evidence of geological processes, differentiation, atmospheres, and moons. Pluto, as revealed by the New Horizons flyby in 2015, has a complex surface with mountains, plains, glaciers of nitrogen ice, and evidence of recent geological activity. This suggests that even in the cold outer reaches of the solar system, worlds can remain geologically active if they are large enough to retain internal heat. Smaller Kuiper Belt objects, those with diameters of tens or hundreds of kilometers, are more purely cometary in nature. They lack the mass necessary for significant geological activity and remain essentially frozen since their formation. When these objects are perturbed into orbits that bring them into the inner solar system, they become the Jupiter family comets we observe, developing comas and tails as solar heating drives sublimation of their surface ices. The scattered disk, a region of space beyond the main Kuiper Belt, contains objects on highly eccentric and inclined orbits. These objects were likely scattered outward by gravitational interactions with Neptune during the solar system's early history. The scattered disk is thought to be the primary source of Jupiter family comets, as objects from this region are more easily perturbed into orbits that enter the inner solar system. Centaurs are another related population of objects orbiting in the region between Jupiter and Neptune. These objects are thought to be in transition between the Kuiper Belt or scattered disk and the inner solar system. Some centaurs show cometary activity despite their relatively large distances from the Sun, suggesting that they contain volatile ices that can sublimate even at low temperatures. The boundary between centaurs and comets is not sharp, but rather represents a continuum of objects with varying activity levels and orbital properties. The Oort cloud, though it has never been directly observed, is inferred with high confidence from the distribution of long-period comet orbits. When astronomers plot the orbital characteristics of long-period comets, they find that these comets have aphelia distributed roughly spherically around the Sun at distances of tens of thousands of astronomical units. This cannot be explained if comets formed in a disk like the Kuiper Belt. It requires a spherical source region, which is what the Oort cloud model provides. The formation mechanism for the Oort cloud involves dynamical processes during the solar system's early history. Computer simulations show that when the giant planets formed and migrated, they ejected vast numbers of planetesimals outward. Most of these planetesimals were ejected completely from the solar system, but some ended up in very distant, weakly bound orbits. Over time, perturbations from passing stars and the galactic tide randomized the orbital inclinations of these distant objects, creating the spherical distribution we call the Oort cloud. The inner Oort cloud or Hills cloud may contain even more comets than the outer Oort cloud, but its objects are even more difficult to detect. They are too distant to be observed directly, and their orbits do not bring them into the inner solar system frequently enough for us to sample them through observations of long-period comets. The inner Oort cloud may represent a transition zone between the scattered disk and the outer Oort cloud, with objects that were not quite ejected far enough to reach the outer cloud, but were perturbed beyond the scattered disk. The question of where comets formed is complex. While the Oort cloud objects likely formed in the region of the giant planets and were ejected outward, the Kuiper Belt objects may have formed closer to their current locations. However, dynamical simulations suggest that significant mixing occurred during planet formation. Objects that formed near Jupiter may have ended up in the Kuiper Belt. Objects that formed beyond Neptune may have been scattered inward and ejected to the Oort cloud. The current locations of comets may not directly reflect where they originally formed. The composition of comets provides clues to their formation locations. The ratio of deuterium to hydrogen in water ice, for example, varies with the temperature at which the ice condensed. By measuring these ratios in different comets, astronomers can infer the temperature conditions where those comets formed. Some comets show deuterium to hydrogen ratios consistent with formation in the cold outer regions beyond 30 astronomical units. Others show ratios suggesting formation at warmer temperatures closer to the Sun. The preservation of comets in cold storage for billions of years is remarkable. In the Oort cloud, temperatures are so low that virtually no chemical reactions occur. The ices remain in the same molecular forms they had when they condensed from the solar nebula. Cosmic rays and solar wind particles occasionally strike the surface of these distant objects, causing some chemical alterations, but the interiors remain pristine, untouched samples of the solar nebula's composition. This makes comets invaluable for understanding the conditions in the early solar system. When we analyze the composition of a comet, we are in effect sampling the solar nebula directly, examining material that has been preserved in a natural deep freeze for 4.6 billion years. No rock sample from Earth, no meteorite, no sample from the Moon or Mars can provide this kind of pristine preservation. Only comets, stored in the cold outer reaches of the solar system, retain such ancient and unaltered material. Throughout human history, certain comets have appeared in Earth's skies with such brightness and prominence that they have been remembered and recorded, their apparitions marking moments in time when the skies offered something extraordinary. Among all the comets that have visited, two stand out for the combination of their beauty, their scientific importance, and their impact on human observers: Halley's Comet and Comet Hale-Bopp. Halley's Comet is perhaps the most famous comet of all. It is named after Edmund Halley, the English astronomer who, in 1705, recognized that comets observed in 1531, 1607, and 1682 were actually the same comet returning on a periodic orbit. Halley calculated that the comet would return again in 1758, and indeed it did, appearing on Christmas Day of that year, 16 years after Halley's death. This was the first time a comet's return had been successfully predicted, proving that comets are members of the solar system orbiting the Sun rather than one-time visitors from interstellar space. The orbital period of Halley's Comet averages about 76 years, though the actual period varies between about 74 and 79 years due to gravitational perturbations from the giant planets, particularly Jupiter and Saturn. This relatively short period means that Halley's Comet returns within a human lifetime, allowing people to potentially see it twice if they live long enough. Halley's Comet has been observed and recorded for more than 2,000 years. Chinese astronomers tracked cometary appearances that can now be identified as Halley's Comet going back to at least 240 BCE. The comet appears in the Bayeux Tapestry, which chronicles the Battle of Hastings in 1066, and its appearance at that time was interpreted by some as an omen of the Norman invasion of England. The nucleus of Halley's Comet is potato-shaped, measuring approximately 15 kilometers by 8 kilometers by 8 kilometers. This makes it larger than many cometary nuclei, but still quite modest in absolute terms. The nucleus rotates with a complex pattern, tumbling rather than spinning smoothly around a single axis. This complex rotation is a consequence of the irregular shape and uneven mass distribution within the nucleus. In 1986, during its most recent return to the inner solar system, Halley's Comet was met by an international fleet of spacecraft. The European Space Agency's Giotto probe flew within 600 kilometers of the nucleus, capturing the first close-up images of a cometary nucleus. The Soviet Vega 1 and Vega 2 probes, Japan's Suisei and Sakigake spacecraft, and NASA's repurposed International Cometary Explorer all contributed to what was called the Halley Armada, a coordinated international effort to study the comet in unprecedented detail. These missions revealed that the nucleus of Halley's comet is extremely dark, with an albedo of just 0.04, darker than coal. They observed jets of gas and dust erupting from active regions on the sunward side of the nucleus, confirming that sublimation is not uniform across the surface but concentrated in specific areas. They measured the composition of the coma and found it dominated by water vapor, with significant amounts of carbon monoxide, carbon dioxide, and various organic molecules. Halley's comet will return again in 2061. At that time, people who were young children during its 1986 appearance will be in their 80s, and a new generation will have the opportunity to witness this famous visitor. The comet will reach perihelion, its closest approach to the Sun, on July 28, 2061. Predictions suggest it will be bright enough to see with the naked eye, though perhaps not as spectacular as some of its historical appearances, which have varied in brightness depending on the comet's exact distance from Earth at the time of perihelion. Comet Hale-Bopp represents a different class of cometary visitor. This was a long-period comet from the Oort cloud, making what may have been only its second passage through the inner solar system. It was discovered independently on July 23, 1995, by Alan Hale and Thomas Bopp, two amateur astronomers in the United States who happened to be observing the same region of sky and noticed a faint, fuzzy object that was not supposed to be there. What made the discovery remarkable was the comet's distance at the time. Hale-Bopp was at a distance of 7.2 astronomical units from the Sun between the orbits of Jupiter and Saturn when it was discovered. Most comets at this distance are far too faint to be detected by amateur observers, but Hale-Bopp was bright enough to see because its nucleus is enormous by cometary standards, estimated to be 60 kilometers in diameter, about 6 times the size of Halley's comet's nucleus, and 4 times the size of the object thought to have caused the extinction of the dinosaurs. As Hale-Bopp continued its inward journey, it steadily brightened. Astronomers were uncertain how bright it would become, because predicting comet brightness is notoriously difficult. Comets can fragment, they can have outbursts that temporarily increase their brightness, or they can simply fail to brighten as much as expected. But Hale-Bopp exceeded most predictions. By early 1997, as the comet approached perihelion, it had become one of the brightest objects in the night sky. At its peak in late March and early April 1997, Hale-Bopp reached an apparent magnitude of about -1.8, brighter than all stars except Sirius, and easily visible even from light-polluted cities. Its twin tails, the white dust tail and the blue ion tail, stretched across more than 40 degrees of sky, about 80 moon diameters. What made Hale-Bopp particularly memorable was not just its brightness, but its longevity. The comet remained visible to the naked eye for 18 months, from May 1996 to December 1997. This is the longest any comet has been visible to the naked eye in recorded history, twice as long as the previous record holder, the Great Comet of 1811. Night after night, month after month, people around the world could step outside and see the comet hanging in the sky, its tails streaming away from the sun, its coma glowing softly against the stars. For astronomers and astronomy enthusiasts, Hale-Bopp was a gift. Telescopes of all sizes were turned toward it. Amateur astronomers photographed it extensively, capturing images that showed intricate spiral patterns in the inner coma, structures in the tails, and the evolution of the comet's appearance as it moved through its orbit. Professional astronomers used advanced instruments to study its composition, discovering molecules that had never been detected in comets before, including argon and krypton, noble gases that provided clues about the temperature conditions in the region where the comet formed. The comet reached perihelion on April 1, 1997, at a distance of 0.914 astronomical units from the Sun. After perihelion, as it began moving outward, it remained visible for months, slowly fading as it receded into the outer solar system. By the end of 1997, it had faded below naked eye visibility, though it remained bright enough for amateur telescopes for several years afterward. Comet Hale-Bopp will not return to the inner solar system for about 2,500 years. Its orbital period was shortened by gravitational interactions with Jupiter during its 1996 to 1997 passage, reducing its period from about 4,200 years to about 2,500 years. When it returns, around the year 4380 or so, human civilization, if it still exists, will witness the comet again, perhaps with instruments and technologies we cannot yet imagine. Both Halley's Comet and Comet Hale-Bopp illustrate the range of cometary behavior. Halley is a short-period comet, returning regularly, its orbit and appearance well documented and predictable. Hale-Bopp is a long-period comet, its appearances rare and unpredictable, its origins in the distant Oort cloud. Yet both are governed by the same physical principles. Both develop comas and tails through sublimation. Both follow orbits determined by gravity and shaped by the giant planets. These famous comets have inspired wonder and curiosity in millions of people. They have appeared in art and literature, in scientific papers and popular articles. They have been observed by professional astronomers with advanced instruments and by amateur observers with binoculars or simply their eyes. They connect us to the broader universe, reminders that we live in a solar system where ancient icy bodies still journey in from the cold darkness to briefly illuminate our skies before returning to the vastness from which they came. The historical impact of Halley's Comet extends far beyond astronomy. Its appearance in 1066, depicted in the Bayeux Tapestry, was interpreted as an omen of the Norman conquest of England. Earlier appearances were recorded by Chinese, Japanese, and Korean astronomers, providing a continuous record of the comet's returns spanning more than 2 millennia. Each appearance has been documented, studied, and remembered, making Halley's Comet the most thoroughly observed periodic comet in human history. The prediction of Halley's Comet's return was a watershed moment in the history of astronomy. Before Edmund Halley's work, comets were thought to be one-time visitors, atmospheric phenomena, or celestial wanderers that appeared once and never returned. Halley's demonstration that the comets of 1531, 1607, and 1682 were the same object, and his successful prediction of its return in 1758 proved definitively that comets are regular members of the solar system, obeying the same laws of motion and gravitation as planets. This discovery had profound implications for our understanding of the cosmos. It showed that the solar system extended far beyond the visible planets, that objects could orbit the Sun in highly elongated ellipses, and that the laws of physics could be used to make accurate predictions about astronomical events years or even centuries in advance. It transformed comets from mysterious omens to predictable celestial mechanics, from objects of superstition to subjects of scientific study. When Halley's Comet returned in 1835 and 1836, astronomers were better prepared to observe it. Improved telescopes allowed more detailed observations of the comet's structure. Photography, though still in its infancy, captured some of the first images of a comet. The comet's return was widely publicized, and many people traveled to dark sites to observe it, beginning a tradition of comet watching that continues to this day. The 1910 return of Halley's Comet generated both excitement and anxiety. Spectroscopic observations had revealed the presence of cyanogen gas in the comet's tail, and some sensationalist news reports suggested that Earth would pass through the tail, exposing the population to poisonous gas. In reality, the gas in cometary tails is so tenuous that no effect was observed when Earth did indeed pass through the tail. The incident highlighted both the public's fascination with comets and the importance of accurate scientific communication. The 1986 return of Halley's Comet was less favorable for Northern Hemisphere observers than some previous returns, as the comet remained relatively far from Earth and low in the sky. However, the opportunity to study the comet with spacecraft more than compensated for the less-than-ideal viewing geometry. The Halley Armada provided unprecedented data, transforming our understanding of cometary nuclei from theoretical models to directly observed realities. Comet Hale-Bopp's discovery story is itself remarkable. Both Alan Hale and Thomas Bopp were experienced amateur astronomers who happened to be observing the same region of sky on the same night. Hale was using his own telescope from his backyard in New Mexico, systematically observing known comets. Bopp was using a friend's telescope at a dark site in Arizona, looking at deep sky objects. Both noticed the fuzzy object near the globular cluster M70, and both realized it was moving, indicating it was a comet rather than a distant galaxy or nebula. The fact that the comet was discovered by amateurs rather than by professional sky surveys speaks to both the dedication of amateur astronomers and to the element of chance in discovery. Had either observer chosen to look elsewhere that night, or had cloudy weather prevented observation, the comet might have remained undiscovered for weeks or months longer, though its brightness would have ensured eventual detection. As Hale-Bopp approached the Sun, professional astronomers turned their instruments toward it in unprecedented numbers. The comet was observed across the electromagnetic spectrum, from radio waves to X-rays. Ground-based telescopes tracked its motion and documented changes in its coma and tails. Space telescopes observed wavelengths blocked by Earth's atmosphere. The Hubble Space Telescope captured high-resolution images showing intricate spiral patterns in the inner coma. The comet's large nucleus made it exceptionally productive in terms of gas and dust output. At its peak activity near perihelion, Hale-Bopp was releasing thousands of kilograms of water vapor per second, along with substantial amounts of carbon monoxide, carbon dioxide, and dust. This high production rate created an enormous coma that was easily visible from Earth and tails that stretched across substantial portions of the sky. One unexpected discovery from Hale-Bopp was the detection of sodium emission in the tail. Previous comets had shown some sodium emission, but Hale-Bopp's was exceptionally strong, creating a distinct yellow-orange tail in addition to the blue ion tail and white dust tail. This sodium tail was visible in photographs and provided new insights into the composition and processes occurring in the comet's coma. The comet's orbit suggests it may have passed through the inner solar system once before, perhaps 4,200 years ago. If so, it may have been observed by ancient civilizations, though no definitive historical records have been identified. The comet's nucleus is large enough and bright enough that it would almost certainly have been visible during any close approach, so the lack of clear historical records may simply reflect the incompleteness of ancient astronomical documentation. When Hale-Bopp returns around the year 4380, human civilization will be profoundly different, assuming it still exists. The technologies we use to observe and study the comet will be unimaginably advanced compared to what was available in 1997. Yet the comet itself will be essentially unchanged, following the same orbit, developing the same coma and tails, responding to the same solar radiation and solar wind, a bridge between the present and a distant future we can barely imagine. We have traveled now through many aspects of comets, from their frozen nuclei to their glowing comas and streaming tails, from their origins in the distant Oort cloud and Kuiper belt to their famous appearances in Earth's skies. At this midpoint in our journey, it seems appropriate to pause and consider the underlying mathematics that governs all of this, the orbital mechanics that determine where comets go and how long they take to get there. An orbit is fundamentally a balance between motion and gravity. A comet, like any object orbiting the Sun, is simultaneously falling toward the Sun due to gravitational attraction and moving sideways fast enough that it continuously misses the Sun. This combination of falling and missing creates the curved path we call an orbit. For planets, these orbits are nearly circular. The distance from the Sun varies by only a few % over the course of an orbit. But for most comets, orbits are highly elliptical, elongated ovals that bring the comet very close to the Sun at one point, called perihelion, and carry it very far from the Sun at the opposite point, called aphelion. The shape of an elliptical orbit can be described by a parameter called eccentricity. A circle has an eccentricity of 0. As the ellipse becomes more elongated, the eccentricity increases toward 1. Cometary orbits typically have eccentricities close to 1, sometimes 0.99 or higher. An eccentricity of exactly 1 would be a parabola, which is not a closed orbit, but rather an escape trajectory. Comets occasionally have eccentricities very slightly greater than 1, indicating hyperbolic orbits that will carry them out of the solar system entirely. The size of an orbit is described by the semi-major axis, which is half the length of the long axis of the ellipse. For a comet with perihelion at 1 astronomical unit from the Sun and aphelion at 100 astronomical units, the semi-major axis would be about 50.5 astronomical units. The orbital period, the time it takes to complete one orbit, is related to the semi-major axis by Kepler's third law, which states that the square of the orbital period is proportional to the cube of the semi-major axis. This means that small orbits are fast and large orbits are slow. Earth, with a semi-major axis of 1 astronomical unit, completes an orbit in 1 year. Jupiter, with a semi-major axis of 5.2 astronomical units, takes about 12 years. A comet with a semi-major axis of 100 astronomical units takes about 1,000 years to complete an orbit. A comet with a semi-major axis of 10,000 astronomical units takes about 1 million years. The speed of an object in an elliptical orbit varies depending on where it is in that orbit. When the comet is at perihelion, closest to the Sun, it is moving at its maximum speed. When it is at aphelion, farthest from the Sun, it is moving at its minimum speed. This variation in speed is a consequence of conservation of energy. As the comet falls inward, gravitational potential energy is converted to kinetic energy, speeding it up. As it climbs back outward, kinetic energy is converted back to potential energy, slowing it down. For a long period comet falling in, from the Oort cloud, the difference in speed between aphelion and perihelion can be enormous. At aphelion, 50,000 astronomical units from the Sun, the comet might be moving at only a few meters per second. At perihelion, perhaps 1 astronomical unit from the Sun, the same comet might be moving at tens of kilometers per second, tens of thousands of times faster. The orientation of a comet's orbit in space is described by several parameters. The inclination describes how tilted the orbit is relative to the plane of the ecliptic, the plane of Earth's orbit. The longitude of the ascending node describes where the orbit crosses the ecliptic plane. The argument of perihelion describes the orientation of the ellipse within the orbital plane. Together, these parameters completely specify the orbit's geometry. Short-period comets from the Kuiper belt tend to have low inclinations, orbiting roughly in the same plane as the planets. This reflects their origin in the flat disk of the Kuiper belt. Long-period comets from the Oort cloud can have any inclination, including retrograde orbits that go around the Sun opposite to the direction the planets orbit. This reflects the spherical distribution of the Oort cloud. Orbits are not perfectly stable over long timescales. Gravitational interactions with the planets can alter a comet's orbit significantly. A close approach to Jupiter, for example, can change a comet's orbital period by years or even decades. Over many orbits, these perturbations accumulate, gradually shifting the comet's path. Some comets are eventually ejected from the solar system entirely on hyperbolic orbits. Others have their orbits circularized, becoming more planet-like. Still others collide with planets or the Sun. The dynamical lifetime of a comet, the time it can continue in its current orbit before gravitational perturbations alter that orbit significantly, is typically only a few million years. This is very short compared to the age of the solar system, 4.6 billion years. The fact that we still observe comets today means they must be continuously supplied from reservoir populations like the Kuiper belt and Oort cloud. All of this orbital mechanics operates according to precise mathematical laws that have been known for centuries. Newton's law of gravitation describes how the force between two bodies depends on their masses and the distance between them. Newton's laws of motion describe how forces produce acceleration. Kepler's laws describe the geometry and timing of elliptical orbits. These laws are deterministic and predictable. Given a comet's position and velocity at one moment, we can calculate exactly where it will be at any future time, accounting for perturbations from planets and other bodies. This predictability is what allows astronomers to calculate when a periodic comet will return, sometimes decades or even centuries in advance. It is what allows spacecraft trajectories to be planned to intercept comets at precise times and locations. It is what transforms comets from mysterious omens into understandable objects whose behavior can be predicted and explained. Yet, for all this mathematical precision, there remains something deeply peaceful about the mechanics of orbits. A comet does not choose its path. It does not strive or struggle. It simply moves according to the forces acting upon it, following the geometry that those forces dictate, tracing out an ellipse in space with patient regularity. Its motion is determined by physics, inevitable and eternal, as unchanging as the laws of nature themselves. And so the comet continues, following its orbit around the Sun, sometimes falling inward into the light and warmth, sometimes climbing outward into the cold and dark, but always bound by gravity, always following the path that mathematics describes, always moving with the quiet certainty of objects obeying natural law. There is comfort in this predictability, in knowing that the universe operates according to rules we can understand, that the motions of comets are not capricious but determined, not random but ordered. As a comet journeys through the inner solar system, trailing gas and dust in its wake, it leaves behind something lasting, something that connects future generations to its passage long after the comet itself has returned to the outer darkness. The dust particles that are pushed away from the comet by solar radiation pressure do not simply vanish. They remain in orbit around the Sun, spreading out along the comet's path, forming a stream of debris that persists for thousands of years. When Earth's orbit carries our planet through one of these debris streams, the result is a meteor shower, one of the most accessible and peaceful astronomical phenomena that anyone can observe. You do not need a telescope. You do not need any equipment at all. You simply need to be outside, under a dark sky, looking up, waiting patiently for streaks of light to appear. These streaks of light, commonly called shooting stars or falling stars, are not stars at all. They are tiny particles, typically no larger than grains of sand, that slam into Earth's atmosphere at tremendous speeds, anywhere from 11 to 72 kilometers per second. At these speeds, friction with the air heats the particles to thousands of degrees. The particles vaporize, creating brief, bright trails of ionized gas that glow for a fraction of a second before fading away. Most meteor shower particles are remarkably small. The majority are less than a millimeter in diameter. Some are only a few hundred micrometers across, about the width of a human hair. Despite their tiny size, their high speed makes them visible from the ground as they burn up in the atmosphere at altitudes of 80 to 120 kilometers. Larger particles, those a few millimeters or centimeters across, create brighter meteors called fireballs, which can be bright enough to cast shadows and occasionally even fragment with audible sounds. Meteor showers occur at predictable times each year because Earth's orbit is fixed relative to the comet debris streams. When we pass through the same region of space each year, we encounter the same debris stream, producing a meteor shower at the same date and time. Different streams produce different showers, each named after the constellation from which the meteors appear to radiate. The Perseid meteor shower, which peaks around August 12th or 13th each year, is one of the most popular and reliable meteor showers. The Perseids are caused by debris from Comet 109P/Swift-Tuttle, a large comet with a nucleus approximately 26 kilometers in diameter. Swift-Tuttle has an orbital period of 133 years and last passed through the inner solar system in 1992. The particles in the Perseid stream were ejected from Swift-Tuttle during previous passages through the inner solar system, some of them perhaps centuries or even millennia ago. They have spread out along the comet's orbit, forming a broad stream that Earth passes through each August. At the peak of the shower, observers in a dark location can see 60 to 100 meteors per hour, a rate of one every minute or two. The radiant of the Perseid meteor shower is in the constellation Perseus, which rises in the northeast in mid-August. Meteors can appear anywhere in the sky, but if you trace their paths backward, they all seem to originate from a point in Perseus. This is a perspective effect, caused by the fact that all the particles are moving in roughly parallel paths as they enter Earth's atmosphere, but from our viewpoint on the ground, perspective makes them appear to radiate from a single point. The best time to view the Perseids, like most meteor showers, is in the hours after midnight and before dawn. This is when your location on Earth is on the leading side of the planet, the side moving forward into the debris stream. It is like driving through rain. You see more raindrops on the windshield in front of you than on the rear window. Similarly, more meteors are visible when you are on the forward-facing side of Earth. The Leonid meteor shower, which peaks around November 17th each year, is caused by debris from Comet 55P/Tempel-Tuttle, which has an orbital period of 33 years. The Leonids are famous for occasionally producing meteor storms, events where the rate of meteors exceeds thousands per hour. These storms occur when Earth passes through particularly dense regions of the debris stream, often shortly after the parent comet has passed through the inner solar system and deposited fresh material. The most famous Leonid meteor storm occurred on the night of November 12th to 13th, 1833, when observers in North America witnessed tens of thousands of meteors per hour. Historical accounts describe the meteors as being so numerous that they fell like snowflakes, and some observers feared that the stars themselves were falling from the sky. This event marked a turning point in the scientific understanding of meteor showers, leading to the realization that they were caused by Earth passing through cometary debris streams. More recent Leonid storms occurred in 1999, 2001, and 2002, shortly after Comet Tempel-Tuttle's perihelion passage in 1998. These storms were well observed by astronomers and produced peak rates of several thousand meteors per hour for brief periods. The next possible Leonid storm is not expected until around 2033, roughly 33 years after the last one, coinciding with the comet's next return to the inner solar system. The Orionid meteor shower, which peaks around October 21st, is caused by debris from Halley's Comet. This is one of two showers associated with Halley. The other is the Eta Aquarid shower in May. The fact that Halley produces two showers is a consequence of Earth's orbit crossing Halley's orbit at two different points. In October, we pass through the part of Halley's orbit where the comet was when it was moving outward from the Sun. In May, we pass through the part where the comet was moving inward. The Orionids typically produce about 20 meteors per hour at peak, and the meteors are known for being quite fast, entering the atmosphere at about 66 kilometers per second. They are also known for producing a significant percentage of persistent trains, glowing trails that can last for several seconds after the initial meteor flash. These trains are caused by the meteors leaving behind ionized gas in the upper atmosphere, which continues to glow briefly before the ions recombine with electrons. The Geminid meteor shower, which peaks around December 13th or 14th, is unusual because its parent body is not a typical comet. Instead, the Geminids are associated with an object called 3200 Phaethon, which is classified as an asteroid, but may actually be an extinct comet that has lost all its volatile ices. Phaethon has an orbit that brings it closer to the Sun than any other named asteroid, at a perihelion distance of only 0.14 astronomical units, closer than the orbit of Mercury. The Geminids are one of the most reliable and intense meteor showers of the year, often producing rates of 120 meteors per hour or more. The meteors are typically bright and colorful, and because the shower peaks in December, viewers in the Northern Hemisphere get to observe it on long winter nights. The radiant is in the constellation Gemini, which rises in the east in the evening and passes overhead around midnight. All meteor showers share certain characteristics. The meteors enter Earth's atmosphere at speeds determined by the geometry of Earth's orbit intersecting the debris stream. The particles burn up at high altitudes, typically never reaching closer than 60 or 70 kilometers from Earth's surface. The entire event, from the time a particle enters the atmosphere to the time it completely vaporizes, lasts only a fraction of a second. And yet, in that brief flash, a particle that may have been ejected from a comet centuries ago, that has been orbiting the Sun patiently ever since, briefly returns to visibility before being converted to vapor and ions. There is something meditative about watching a meteor shower. You lie on your back, looking up at the sky, waiting. Minutes may pass with nothing. Then suddenly, a streak of light flashes across your peripheral vision. Then another. Then perhaps several minutes of nothing before the next one. There is no way to predict exactly when or where each meteor will appear. You cannot control the rate. You can only wait, watch, and appreciate each brief flash when it comes. The particles themselves came from comets, bodies that formed billions of years ago in the outer reaches of the solar nebula. They were ejected when those comets approached the sun and developed comas and tails. They spread out along orbital paths that eventually intersected Earth's orbit. And now, thousands of years after their ejection, they briefly shine in Earth's atmosphere, visible reminders of the comets that released them, connecting us across time to ancient events in the history of the solar system. Understanding the parent comets of meteor showers reveals fascinating details about how long these debris streams persist. Comet Swift-Tuttle, the parent of the Perseids, last passed through perihelion in 1992, yet the Perseid stream contains particles ejected over hundreds or thousands of previous orbits. The stream has had time to spread and evolve, with particles dispersed over millions of kilometers along the comet's orbital path. The oldest particles in the stream may have been ejected centuries ago, during passages when no human observed the comet when it approached the sun in silence and returned to darkness without witness. The Taurid meteor shower complex represents an even more ancient and dispersed debris stream. Associated with Comet 2P/Encke and possibly with larger bodies that broke apart thousands of years ago, the Taurids actually consist of two separate branches, the northern Taurids and southern Taurids, which peak at slightly different times in October and November. The stream is so broad that Earth takes several weeks to pass through it completely, resulting in a prolonged period of meteor activity rather than a sharp peak lasting only a day or two. Some researchers have suggested that the Taurid complex may contain larger debris, including meteor-sized or even larger fragments that could potentially pose a hazard to Earth. While most meteor shower particles are harmless, burning up completely in the atmosphere, larger objects could survive atmospheric entry and reach the surface as meteorites. So far, no confirmed meteorites have been linked to meteor showers, but the possibility remains an area of active research. The quadrantid meteor shower, which peaks around January 3rd or 4th each year, is associated with an object called 2003 EH1, which may be an asteroid, an extinct comet, or possibly a rock comet, an object that exhibits some cometary characteristics without developing a significant coma. The quadrantids are notable for having a very sharp peak, with maximum rates lasting only a few hours rather than a day or more, as with other major showers. This suggests that the debris stream is relatively narrow and concentrated rather than being spread out over a wide region of space. Each meteor shower has its own characteristics, its own rhythm and pattern. Some produce steady rates throughout their active period. Others show variations in activity from year to year, possibly due to encountering denser filaments within the stream or to gravitational perturbations that shift the stream's position relative to Earth's orbit. Long-term observations of meteor showers, extending back decades or even centuries, reveal these patterns and help astronomers understand how debris streams evolve over time. Historical records of meteor showers provide valuable information about past cometary activity. The Chinese have kept records of astronomical phenomena for more than 2,000 years, including observations of particularly intense meteor displays. By correlating these historical observations with known meteor showers and their parent comets, astronomers can sometimes identify the timing of previous orbital returns and improve their understanding of how cometary orbits have changed over time. The process by which meteor shower particles are ejected from comets is not uniform. Particles released when the comet is near perihelion receive more velocity from the sublimating gas than particles released farther from the Sun. Particles released on the sunward side of the nucleus follow slightly different trajectories than particles released from the sides or the nightward side. Over time, these differences in ejection velocity and direction cause the particles to spread throughout the stream, creating the extended debris trails we encounter during meteor showers. Watching meteor showers connects us not only to the comets that produce them, but also to countless other observers throughout history who have witnessed the same annual displays. Ancient civilizations saw the Perseids and Leonids, though they may not have understood what caused them. Medieval astronomers recorded unusually bright meteor displays, not knowing they were witnessing storm events. Modern observers, armed with understanding but still capable of wonder, continue the tradition of looking up, of noting the streaks of light, of appreciating these small fragments from distant bodies making their final, brilliant appearance. There is a rhythm to the meteor. Shower calendar, a cycle of annual events that provides structure to the observing year. Spring brings the Lyrids in late April. Summer brings the Perseids in August. Fall brings the Orionids in October and the Leonids in November. Winter brings the Geminids in December and the Quadrantids in January. Throughout the year, these showers come and go, each one a reminder that Earth is constantly moving through space filled with debris from ancient comets, each one an opportunity to witness the transformation of matter from solid particle to glowing plasma. And yet, for all the predictability of meteor showers, each individual meteor remains unpredictable. You cannot know when the next one will appear. You cannot know how bright it will be, how long its trail will persist, whether it will fragment or produce a persistent train. Each meteor is unique, a one-time event that will never be repeated in exactly the same way. This combination of predictable pattern and unpredictable detail makes meteor watching both meditative and surprising, both calming and occasionally exciting, a perfect activity for quiet contemplation under dark skies. For most of human history, comets could only be observed from Earth, their details hidden by distance and obscured by the brightness of their comas. But beginning in the late 20th century, humanity developed the capability to send spacecraft to comets, allowing us to study these objects up close and revealing details that could never be observed from Earth. The first close encounter between a spacecraft and a comet occurred in 1985 and 1986, when an international armada of spacecraft flew past Halley's Comet during its return to the inner solar system. The European Space Agency's Giotto probe made the closest approach, flying within 600 kilometers of the nucleus on March 14, 1986. Giotto's cameras captured the first images of a cometary nucleus, revealing a dark, potato-shaped body approximately 15 kilometers long and 8 kilometers wide. The images showed a surface covered with a dark crust, punctuated by bright jets of gas and dust erupting from active regions on the sunward side. The nucleus was rotating with a period of about 52 hours, causing these jets to sweep across space like the beam of a lighthouse. The spacecraft's instruments measured the composition of the coma, confirming that water vapor was the dominant component, making up about 80% of the gas. Carbon monoxide and carbon dioxide, accounted for most of the remainder, with smaller amounts of methane, ammonia, and various organic molecules. The dust particles were found to be a mixture of silicate minerals and organic compounds, with individual particles ranging in size from fractions of a micrometer to tens of micrometers. Giotto's encounter with Halley was brief and violent. The spacecraft was traveling at a relative velocity of 68 kilometers per second, and even tiny dust particles at that speed carried tremendous energy. Seconds before closest approach, a large dust particle struck the spacecraft, knocking it off its pointing direction and temporarily interrupting communications with Earth. The spacecraft survived but was severely damaged by hundreds of impacts with dust particles during its few minutes in the inner coma. In 1999, NASA launched the Stardust spacecraft with the mission of flying past Comet 81P/Wild 2 and collecting samples of cometary dust for return to Earth. The encounter occurred on January 2, 2004, when Stardust flew within 236 kilometers of the nucleus. During the flyby, the spacecraft extended a collector filled with a substance called aerogel, a lightweight foam with a density only a few times that of air, designed to capture dust particles without destroying them. The spacecraft successfully collected thousands of tiny dust particles and returned them to Earth in January 2006, making Stardust the first mission to return samples from beyond the orbit of the Moon. Analysis of these particles revealed that they contained a mixture of crystalline silicates and organic compounds. Surprisingly, some of the particles contained minerals that could only have formed at very high temperatures, suggesting that material from the hot inner solar nebula was somehow transported to the cold outer regions where comets formed. NASA's Deep Impact mission, launched in January 2005, took a more aggressive approach to studying comets. The mission consisted of a flyby spacecraft and an impactor probe. On July 4, 2005, the impactor slammed into Comet 9P/Tempel 1 at a relative velocity of 10 kilometers per second. The collision excavated a crater and ejected a huge plume of material from beneath the comet's surface. Cameras on the flyby spacecraft recorded the impact and the resulting ejecta. Analysis of the material thrown up by the impact revealed that the subsurface of the nucleus was richer in ice than the surface, suggesting that a layer of ice lies beneath the dark crust. The impact also revealed that the nucleus was much less dense and more porous than expected, described by mission scientists as more like a snowbank than a solid iceberg. The most ambitious and successful comet mission to date has been the European Space Agency's Rosetta mission, which launched in March 2004 with the goal of orbiting Comet 67P/Churyumov-Gerasimenko and landing a probe on its surface. After a 10-year journey that included several flybys of Earth and Mars to gain the velocity needed to reach the comet, Rosetta arrived at 67P in August 2014. Rosetta spent more than 2 years orbiting the comet, studying it from close range as it approached and passed perihelion. The mission revealed a nucleus with a remarkable duck shape, 2 distinct lobes, connected by a narrow neck region. High-resolution images showed a surface covered with varied terrain, including smooth dust-covered plains, boulder fields, cliffs, pits, and active regions where jets of gas and dust erupted. In November 2014, Rosetta deployed the Philae lander, which successfully touched down on the comet's surface, becoming the first spacecraft to land on a comet. The landing was more dramatic than planned. Philae's anchoring harpoons failed to deploy, and the lander bounced twice before settling in a location that was shadowed and unfavorable for solar power generation. Nevertheless, Philae operated for about 60 hours on its primary battery, conducting a series of experiments that provided valuable data about the comet's surface composition and structure. Rosetta's instruments measured the composition of the coma in detail, confirming that water was the dominant volatile, but also detecting significant amounts of carbon dioxide, carbon monoxide, and complex organic molecules. One surprising finding was that the ratio of deuterium to hydrogen in the comet's water was about 3 times higher than in Earth's oceans, suggesting that comets like 67P may not have been the primary source of Earth's water. The mission tracked the comet's activity as it approached and passed perihelion in August 2015. Rosetta observed dramatic increases in gas and dust production, with jets erupting from specific locations on the nucleus, particularly from the neck region between the 2 lobes. The spacecraft documented the formation and evolution of the coma and tails, providing unprecedented views of how a comet responds to increasing solar radiation. In September 2016, at the end of its mission, Rosetta was commanded to descend to the comet's surface, making a controlled impact that brought the spacecraft to rest on the object it had orbited for more than 2 years. The descent provided close-up images of the surface at resolutions of a few centimeters per pixel, revealing textures and structures that could not be seen from orbital altitudes. These spacecraft missions have transformed our understanding of comets. Before the missions, comets were mysterious objects known only from telescopic observations. After the missions, they became real places with complex geology, active processes, and detailed compositions. We have seen their surfaces, measured their properties, and even touched them with our instruments. Yet for all that these missions have revealed, comets remain fascinating objects. Each new mission discovers something unexpected. Each comet visited turns out to have its own unique characteristics. The diversity among comets suggests that they formed in different regions of the solar nebula under different conditions and have experienced different histories since their formation. Future missions will continue this exploration. There are plans to return samples from a Breddington comet's nucleus, drilling beneath the dark surface crust to retrieve pristine ice from the interior. There are proposals to orbit comets for longer periods, following them through multiple orbits to understand how they evolve over time. There are even concepts for landing on comets and establishing long-term observatories that could monitor their activity continuously. But for now, we can appreciate what has already been accomplished. A handful of spacecraft have traveled millions or billions of kilometers to visit these ancient objects. They have sent back images and data that have revolutionized our understanding. They have shown us what comets truly are, validating some theories, overturning others, and raising new questions for future missions to answer. And, in doing so, they have brought comets from the realm of distant observation into the realm of direct exploration, making these ancient wanderers not just objects to study from afar, but places we can visit, touch, and know. As we near the end of our journey through the realm of comets, let us gather together some of the quieter facts, the characteristics that speak to the peaceful, patient nature of these ancient bodies. These are not dramatic revelations, but rather simple truths about how comets exist and behave, facts that invite contemplation rather than excitement. A comet in the Oort cloud, 50,000 astronomical units from the Sun, is moving at a velocity of only about 10 meters per second. This is slower than a car on a highway. At this speed, it would take the comet more than 150,000 years to travel 1 astronomical unit, the distance from Earth to the Sun. The comet is in no hurry. it has billions of years ahead of it. Time passes differently at such distances, measured not in seconds or hours, but in millennia and epochs. The temperature of a cometary nucleus in the Oort cloud hovers around 40 Kelvin, or minus 233 degrees Celsius. This is cold, beyond ordinary experience, so cold that all familiar substances except helium would be frozen solid. At this temperature, molecular motion is minimal. Atoms vibrate within their crystal structures but barely move. The ice is hard, stable, unchanging. It could remain in this state essentially forever if not for the slow, inexorable pull of gravity drawing the comet inward. The rotation period of cometary nuclei varies widely, but many rotate with periods of several hours to several days. Comet 67P/Churyumov-Gerasimenko, for example, has a rotation period of about 12 hours. This is similar to Earth's rotation period, but unlike Earth, which rotates smoothly around a well-defined axis, 67P tumbles in a complex pattern. Different parts of the surface experience day and night at different times, creating patterns of heating and cooling that vary from one rotation to the next. The escape velocity from a typical cometary nucleus is measured in meters per second, not kilometers per second, as it is for planets. A 5-kilometer radius nucleus with a density of 600 kilograms per cubic meter has an escape velocity of about 1.5 meters per second. This is slow enough that a person could literally jump off the surface and escape into space. The nucleus's gravity is so weak that it can barely hold onto its own material, much less maintain an atmosphere or capture passing debris. The albedo of cometary nuclei, as mentioned earlier, is typically around 0.03 to 0.04. This makes them darker than almost any material found on Earth. Fresh asphalt has an albedo of about 0.07. Deep ocean water has an albedo of about 0.06. Only materials like activated charcoal or certain volcanic rocks approach the darkness of cometary surfaces. The porosity of cometary nuclei means that they contain significant empty space within their structure. If you could compress a cometary nucleus to remove all the voids and gaps, it might shrink to perhaps 70 or 80% of its original volume. This means that about 20 to 30% of the nucleus's volume is literally nothing, just empty space between grains of ice and dust. This gives the nucleus a fragile, delicate structure that can be easily disrupted. The rate of sublimation from a cometary nucleus when it is active varies with distance from the Sun, but typically ranges from hundreds to tens of thousands of kilograms per second. To give this some context, the flow rate of water over Niagara Falls is about 2.4 million kilograms per second, hundreds of times greater than even the most active comet. The water flowing over Niagara in a single second is equivalent to the material a typical comet might sublimate in several minutes. The composition of cometary ice includes not just water, but a mixture of frozen volatiles. The relative abundances vary from comet to comet, but typical ratios might be 80% water ice, 10% carbon monoxide, 5% carbon dioxide, with the remaining 5% consisting of methane, ammonia, and various other compounds. This composition reflects the conditions in the solar nebula where comets formed with different volatiles, condensing at different temperatures and distances from the Sun. The dust-to-ice ratio in cometary nuclei is typically around 1 part dust to 3 or 4 parts ice by mass. This means that for every kilogram of dust in the nucleus, there are 3 or 4 kilograms of ice. As the ice sublimates away over many orbits, This dust accumulates on the surface, gradually building up the dark crust that covers most cometary nuclei. Over time, some comets may become more dust-rich as their surface ice is depleted. The orbital periods of short-period comets, those with periods less than 200 years, are measured in years or decades. Comet Encke, which has the shortest known orbital period of any comet, completes an orbit in just 3.3 years. Halley's Comet, as mentioned, has a period averaging 76 years. These relatively short periods mean that the comets return regularly and can be observed multiple times by professional astronomers and amateur enthusiasts alike. The orbital periods of long-period comets can extend into millions of years. Some comets appear to be on nearly parabolic orbits with periods so long that they are effectively indistinguishable from infinity. These comets may take millions of years to return to the inner solar system, or they may be making their first and only visit before being perturbed onto hyperbolic trajectories that will carry them out of the solar system forever. The number of comets in the Oort cloud is estimated to be in the trillions, perhaps between 1 trillion and 10 trillion individual bodies. If we assume an average mass of 10 to the 14 kilograms per comet, roughly the mass of a 1-kilometer radius nucleus, the total mass of the Oort cloud would be between 1 and 10 Earth masses. This is a significant reservoir of material, but it is spread over such an enormous volume of space that the density is incredibly low. The average distance between comets in the Oort cloud is likely millions of kilometers or more. Even though the Oort cloud contains trillions of objects, the volume it occupies is so vast that collisions between comets are extraordinarily rare. Each comet orbits the Sun in isolation, separated from its nearest neighbors by distances far greater than the Earth-Moon distance. It is a realm of profound solitude. The lifetime of a short-period comet, the time it can continue sublimating and developing comas and tails before exhausting its volatile ices, is typically a few thousand orbits. For a comet with an orbital period of 10 years, this corresponds to tens of thousands of years of active life. For a comet with a period of 100 years, it corresponds to hundreds of thousands of years. This is long by human standards, but brief in the context of the solar system's 4.6 billion-year history. The dynamical lifetime of comets, the time before gravitational perturbations significantly alter their orbits, is typically only a few million years. This is why the Oort cloud and Kuiper belt are necessary. Without these reservoirs continually supplying new comets to the inner solar system, all the short-period comets we observe today would have been lost billions of years ago, either ejected from the solar system, colliding with planets or the Sun, or having their volatile ices exhausted. The magnetic field of cometary nuclei appears to be negligible or non-existent. Measurements from the Rosetta mission found no detectable magnetic field around the nucleus of Comet 67P, suggesting that comets did not retain significant magnetic minerals from the solar nebula, or that any magnetic minerals present are randomly oriented and produce no net field. This is consistent with comets forming through gentle accretion rather than through high-temperature processes that might align magnetic minerals. The gravitational interactions between comets and planets can alter cometary orbits significantly. A close approach to Jupiter can change a comet's orbital period by years or even centuries. In some cases, comets have been observed to fragment due to tidal forces during close planetary approaches. In other cases, comets have been captured into orbit around planets, as happened with Comet Shoemaker-Levy 9, which was captured by Jupiter and then collided with the planet in July 1994. The total number of known comets is several thousand, But this represents only a tiny fraction of the comets that actually exist. Most comets are too faint to be detected from Earth, even with powerful telescopes, unless they happen to come close enough to the Sun to develop bright comas. Automated surveys are gradually discovering more comets, particularly as improved cameras and data processing techniques allow detection of ever fainter objects. All of these facts, taken together, paint a picture of comets as ancient, patient travelers following orbits that may span millions of years, occasionally venturing close enough to the Sun to briefly develop the spectacular displays that make them famous, but spending most of their existence in cold, dark solitude, unchanged and unchanging, waiting for the slow pull of gravity to draw them inward once more. They are not active participants in the solar system's drama, but rather quiet witnesses, carrying within themselves records of the solar system's formation, preserving in their icy hearts materials that have remained largely unaltered for billions of years. The silence of comets in deep space is absolute. There is no sound in the vacuum. There are no collisions producing noise. There is only the radiation of electromagnetic waves, the gentle pressure of starlight, and the inexorable pull of gravity. A comet could orbit for 1,000,000 years without experiencing any event that might be called dramatic, without any change in its condition, simply tumbling through the void in perfect quietude. The stability of cometary orbits, even over very long timescales, is remarkable considering the many gravitational influences at work. The Sun exerts the dominant force, but distant stars occasionally pass close enough to perturb orbit slightly. The galactic tide, the differential gravitational force exerted by the galaxy as a whole, also has a subtle effect on the most distant objects. Yet despite these perturbations, most cometary orbits remain stable for millions of years, changing only gradually, almost imperceptibly, from one orbit to the next. The evolution of a comet over many orbits is a study in gradual transformation. Each passage through the inner solar system removes a thin layer from the surface, perhaps a few centimeters or tens of centimeters, depending on how close the comet approaches the Sun and how active it is. Over hundreds of passages, this erosion can significantly alter the surface, exposing deeper layers, changing the pattern of active regions, gradually reducing the total mass of the nucleus. Some comets show evidence of this evolution in their changing activity levels. Comet Halley, for example, has been observed for more than 2,000 years, and historical records suggest that its brightness has varied significantly over different apparitions. Some of this variation is due to changing geometric conditions, how close the comet passes to Earth, and at what angle we observe it. But some of the variation may be due to changes in the comet itself, depletion of volatiles in some regions, accumulation of dust mantles in others, gradual evolution of the nucleus over many passages. The dust that accumulates on cometary surfaces has its own story. Each grain represents material that was once embedded in ice, carried, along as the comet formed 4.6 billion years ago. When the ice sublimates, the dust is left behind, grain by grain, layer by layer, slowly building up the dark crust we observe. This crust insulates the underlying ice, slowing further sublimation, creating a negative feedback loop that tends to reduce activity over time as more and more of the surface becomes mantled. The color of comets, when observed through telescopes with sensitive instruments, reveals information about their composition and history. The nucleus itself appears dark and reddish in color, consistent with the presence of complex organic compounds. The dust in the coma and tail appears yellowish or whitish, reflecting the color of sunlight. The gas coma can show various colors: green from diatomic carbon, blue from ionized carbon monoxide, and red from certain organic molecules. These colors, though subtle, tell stories about what molecules are present and how they interact with solar radiation. The jets and outbursts observed on active comets are not random but appear to be controlled by the comet's rotation and by the distribution of active areas on the surface. As the nucleus rotates, active regions are carried into and out of sunlight, turning jets on and off with a regular periodicity. Some comets show stable, long-lived jets that persist for weeks or months. Others show more variable behavior, with jets appearing and disappearing, changing strength and direction, responding to changes in the surface or subsurface that we cannot directly observe. The fate of comets varies. Some are eventually ejected from the solar system on hyperbolic orbits, flung outward by gravitational encounters with Jupiter or other planets. These objects become interstellar comets, wandering through the galaxy until perhaps billions of years in the future they might encounter another star system. Some comets collide with the Sun, plunging into the solar atmosphere where they are completely vaporized. Some collide with planets, as Shoemaker-Levy 9 did with Jupiter, and some simply exhaust their volatiles and become dormant, indistinguishable from asteroids except by their orbits. The chemistry preserved in comets is a window into the conditions of the early solar nebula. Different molecules condense at different temperatures, so the presence or absence of specific compounds tells us about the temperature where the comet formed. The isotopic ratios in cometary ices, the relative abundances of different isotopes of hydrogen, oxygen, carbon, and nitrogen, provide clues about mixing and transport in the solar nebula. Some comets show evidence of having incorporated materials from very different regions of the nebula, suggesting that mixing was efficient during planet formation. The organic molecules found in comets range from simple compounds like methane and formaldehyde to complex molecules with dozens of atoms. Some of these molecules are precursors to biological molecules, compounds that on Earth are associated with life. The delivery of these organic compounds to the early Earth via cometary impacts may have contributed to the origin of life, providing the chemical building blocks from which biology eventually emerged. This makes comets not just interesting astronomical objects, but potentially crucial players in the history of life itself. The water in comets is chemically similar to water on Earth, with the important exception of the deuterium to hydrogen ratio. Different comets show different ratios, suggesting they formed in different regions of the solar nebula or incorporated different mixtures of ices. Some comets have deuterium to hydrogen ratios similar to Earth's oceans, suggesting they could have delivered water to our planet. Others have significantly different ratios, suggesting they are not likely sources of Earth's water. The diversity among comets reflects the diversity of conditions in the early solar system. The study of comets continues to reveal new surprises. Each mission to a comet discovers unexpected features, challenges existing models, and raises new questions. The Rosetta mission, for example, found that the surface of Comet 67P was far more diverse and complex than expected, with distinct geological units, layers, and structures that suggest a complex formation and evolution history. These discoveries remind us that, despite decades of study, comets still have secrets to reveal, still have lessons to teach about the formation and evolution of our solar system. We have journeyed now through the realm of comets, from their frozen cores to their glowing comas and streaming tails, from the distant reservoirs of the Oort cloud and Kuiper belt to their spectacular but brief appearances in Earth's skies. We have explored the physics of sublimation and the mechanics of orbits, the famous visitors remembered throughout history, and the spacecraft that have ventured out to study these bodies up close. And throughout this journey, a certain character has emerged, a sense of the quiet, patient nature of these ancient wanderers. Comets do not rush. They follow their orbits at speeds determined by gravity and distance, sometimes moving barely faster than a walking pace in the outer reaches of their trajectories, sometimes plunging through the inner solar system at tens of kilometers per second, but always following the path that physics dictates, always responding to forces rather than choosing directions. There is no agency in their motion, no purpose or goal. They simply are, and they move, and that movement has continued for billions of years without change or deviation from natural law. The transformation of a comet as it approaches the sun is gradual, measured in weeks and months rather than moments. The sublimation begins slowly, almost imperceptibly at first, as temperatures rise and the most volatile ices begin to turn from solid to gas. The coma grows steadily, fed by escaping molecules, expanding into the vacuum of space without sudden boundaries or sharp transitions. The tails develop and lengthen as more material is released and as radiation pressure and solar wind act upon that material. But even this development is patient, measured, continuous. When we observe a bright comet in Earth's sky, hanging above the horizon after sunset or before dawn, its tails streaming away from the sun, we are seeing the result of processes that have unfolded over months or years as the comet fell inward from the outer solar system. The light we see left the comet minutes ago, having traveled across the distance that separates it from Earth at the speed of light. The coma we observe is made of molecules that escaped from the nucleus hours or days earlier, having been carried outward by sublimation and now reflecting and emitting sunlight. And the nucleus itself, the source of all this activity, is a small, dark body that has existed for 4.6 billion years, formed in the cold outer reaches of the solar nebula from the same materials that eventually accreted to form the planets, preserving within its icy structure a record of those ancient conditions. When we study comets, we are reaching back in time to the era of solar system formation, examining materials that have remained largely unchanged across the vast span of geological time. There is something profoundly calming about this perspective. In an era where much of life seems to move at an accelerated pace, where information flows instantly and events unfold rapidly, comets remind us that the universe operates on different timescales. A cometary orbit may take thousands or millions of years to complete. The journey from the Oort cloud to the inner solar system can take longer than human civilization has existed. The frozen ices in a cometary nucleus have waited 4 billion years or more for the warmth of the sun to release them into space. These timescales invite patience. They suggest that some processes cannot be rushed, that some journeys must unfold at their own pace, that some changes occur so gradually that they are imperceptible from one moment to the next, but undeniable over long spans of time. The comet does not hurry. It cannot hurry. It moves at the speed gravity allows, following the orbital path that physics dictates, arriving at perihelion exactly when orbital mechanics predicts, neither early nor late. And when the comet's brief period of visibility is over, when it has passed perihelion and begins its long journey back out to the cold darkness from which it came, there is no sense of loss or ending. The comet will return, if it is a periodic comet, in its own time, following the same orbital path, responding to the same gravitational forces. Its absence is not permanent, but temporary, measured in decades or centuries, but ultimately finite. The cycle continues as it has continued for billions of years, as it will continue for billions more. For those who have found this exploration relaxing, who have allowed these facts and figures to wash over them without stress or urgency, the lesson of comets is clear. There is peace in patient processes, in gradual changes, in following natural paths without resistance. The comet does not resist gravity. It does not struggle against the forces acting upon it. It simply moves, and in that movement there is a kind of grace, a flowing response to natural law that requires no effort because it is effortless, no choice because it is inevitable. As you rest now, as your mind perhaps drifts towards sleep or deeper relaxation, you might carry with you the image of a comet in deep space, tumbling slowly, following its orbit through the darkness, patient and unchanging, waiting for its distant perihelion when it will briefly shine before returning once more to the cold outer reaches from which it came. There is no urgency in this image, no demand for attention or action. There is only existence, continued and continuing, as inevitable and peaceful as the stars themselves. If you have enjoyed this journey through the realm of comets, if you have found value in these quiet facts and gentle explorations, I invite you to like this video and subscribe to the channel. There are many more topics to explore in the universe, many more subjects that lend themselves to this kind of calm, detailed examination. By subscribing, you ensure that you will be notified when new content becomes available, new journeys through the cosmos that might accompany your rest or your quiet moments of contemplation. The act of subscribing takes only a moment, just a click, but it helps the channel continue to produce content, to explore new topics, to provide these peaceful explorations for others who might seek them out. If this video has served its purpose, if it has provided the relaxation or the information you were seeking, that small gesture of support would be appreciated. Thank you for spending this time exploring comets. Thank you for your patience with the details, your willingness to move slowly through facts and figures, your openness to a topic that unfolds not with drama, but with quiet persistence. May you rest well, and may the patient orbits of ancient comets remind you that not everything must rush, that some of the most profound processes in the universe unfold slowly, steadily, inevitably, following paths laid out by natural law billions of years ago and continuing still. The comets continue their journeys through the darkness. We have paused to observe them, to learn from them, to appreciate their quiet beauty. And now, as they continue, and as we too continue, there is a connection, a shared existence in a universe governed by the same physical laws, moving through time together, each following our own paths, each responding to forces beyond our control, each part of the vast, patient, eternal unfolding of cosmic history. Rest now, knowing that the universe continues its slow, majestic dance, and that somewhere in the darkness, ancient wanderers continue their patient orbits, unchanged and unchanging, timeless travelers in the endless void.